time for a talk. And the speaker now is Eyal Goren, and he's going from McGill, yes. Well, I looked and saw Udi's, that Udi was from Hebrew, and I thought, wait, what happened? Okay, so this is Eyal Goren, and he's going to speak on foliations on Shimura varieties. Go ahead, Eyal.
Thank you, Jim, for the introduction, and thanks to all the organizers for the opportunity to speak in this wonderful conference. My talk is about foliations on Shimura varieties. It has to do with the geometry in characteristic P, in positive characteristic of Shimura varieties. And certainly the structure of Shimura varieties in characteristic P and even periodically is of great interest to Steve, well, generally because of the connection to the Kudla program. But today, this morning, we heard from Michael Rappaport about their work together with Thomas Zink about periodic uniformization. So certainly, I think it's a subject that is of interest to him, but I was hard pressed to find any direct link between my talk and Steve's work. So in particular, there are no theta functions, so theta correspondence. There's a theta operator, but I don't know if this really counts. So I thought, well, at least I'll try and find a picture, which many have done. And I discovered that I have exactly one picture of Steve, but in fact, it couldn't be more perfect. So let me show it to you. So here we see this picture is taken in Barbados, where we held many conferences. Steve participated in several of them and helped organize them and spoke in them. It was a great presence in these activities. We see Steve and his wife, Selmaz. And also, happily enough, my co-author, Udi the Shalit, appears here. So just a perfect opportunity. Okay, so let me move to business. So I'm going to talk about foliation. I'm going to start with some introduction to the topic of foliation and then explain how we use this in the study of Shimura varieties in characteristic P. Okay, so I will actually focus on two examples today, the Hilbert modular varieties and unitary Shimura varieties, examples that are familiar and often used in the context of also of Steve's work. And we hope that we'll be able to extend all this work at least to the context of simple Shimura varieties in Kotwitz sense, but there's still a lot of work to be done to get there. And my goal is to explain two kinds of foliations on these examples. I will use the Hilbert modular varieties to explain one sort of foliations, and unitary Shimura varieties to explain another source of foliations. Okay, so to begin with, let me define what a foliation is. So let S be any non-singular variety of an algebraically closed field K that could be of characteristic P or 0, actually. So the first requirement, a foliation is a subbundle of the tangent bundle of the variety. Now, the tangent bundle, if we think about it as a sheaf of derivations, it has a structure of a Lie algebra, or sheaf of Lie algebras. Namely, if we think about sections of T of the tangent bundle as derivations, we could calculate their Poisson brackets, namely compose them in two different ways and take the difference. That's another derivation. And the first condition we put about F is that it's involutive, namely that it's closed under those Poisson brackets. We also want it to be a saturated subsheaf. So if we take the quotient of T modulo F as an OS module, it should be torsion-free. And in characteristic 0, that's where it stops. That's the whole definition of a foliation. In characteristic P, the Lie algebra, the tangent bundle has another property that it's so-called P-closed. So when you have a derivation in characteristic P, if you iterate it P times, it turns out to be a derivation once more. It's not true in characteristic 0, but it's true in characteristic P. And we require that F is also closed under this P power operation, okay? So there's some sort of lack of uniformity in the definition between characteristic 0 and characteristic P. Okay, so when those conditions hold, depending on the characteristic of K, we say that F is a foliation, and we call it smooth if it's locally everywhere of a direct summand of T, and not just generically so. Okay. So as to the motivation of studying foliation, it really comes from two different sources. It's a huge subject in the study of geometry and topology of differential manifolds or hyperbolic manifolds, study of differential equations. I recently checked on MathSciNet and found that there are about 3,500 papers with foliation appearing in the title, but in contrast, there are only 55 where foliation appears in the title, and they're also under the subject code 14 of algebraic geometry. So there's much to do about this subject in the context of algebraic geometry. One reason this is such an important notion that given a foliation in characteristic 0, say over the complex numbers, gives you an interesting geometrical or topological information about your manifold. For example, Frobenius theorem says that whenever you have a smooth foliation F on a complex variety S, it's integrable, namely given a point on this variety, there is an analytic subvariety passing through this point, such that the tangent bundle of this variety agrees with the foliation. Okay, so in fact, because of this theorem, there are two ways to think about foliations in characteristic 0. One is the way I define it. The other one is dividing the manifold into sort of parallel, in quotes, analytic subvarieties that altogether cover the manifold. Okay, and the interesting point is that even if S, the variety, the foliation, and the point are algebraic, this leaf of the foliation passing through X is most often transcendental and not algebraic. And we'll see this example already for Hilbert modular surfaces. Okay, see this phenomena. Okay, now there's another completely different source of motivation to study foliation, and that's really where we come into that. But before, let me give you one particular example. So this is due to TNGs. Let's take A to be a simple complex abelian surface. Then given any tangent vector at the origin, I can just translate it over the whole abelian surface using the group structure and get this way a non-vanishing vector field that I can just saturate to get a foliation, a sub-bundle of the tangent bundle, which is also involutive. And if A is simple, there are no other smooth foliations. That's somehow the whole source of foliations on a complex abelian surface. But if A is not simple, if it's isogynous to a product of two elliptic curves, there are other foliations called turbulent foliations. I'm not going to define them here. I'm just going to say that they are reminiscent of the so-called Reb foliations on real two-dimensional tori. Okay, so if I have a real two-dimensional tori, which we draw as a square with identify opposite edges, there are first the linear foliations, the one I discussed here. Given a tangent vector, you can sort of promote it to a foliation of the whole surface. But there are also other things you can do. You can define this torus into strips, so to say, and define on each strip this kind of different foliation where you glue opposite sides. In fact, not necessarily in a linear, perfect linear way, but you can identify opposite sides using a diffeomorphism this interval and get more complicated structures. And in fact, you can also get foliations of this sort, and this is really what called the Reb foliations. So again, I'm just kind of giving some sort of intuition about the richness of the subject. I'm not really getting into the details here. So Etienne's paper is a great source to learn about that.
Yeah, these examples that you gave, you can do them also in the algebraic setting, not only in the transcendental.
Yes, yes. So GIS is really in an algebraic setting. Okay. And here, just to give an indication of what's going on, I'm drawing the analog for two-dimensional real tori. Okay, so.
Does this example work for higher than two-dimensional?
Yes, definitely this kind of linear foliations works in quite generality, and also this, as long as you're over the complex numbers. In characteristic P, we know much less at this point.
So for any complex abelian varieties of arbitrary dimension, this works?
Yeah.
Okay, thanks.
Yeah, definitely. Okay, so I should just mention some modern contributors to foundations of sort of foliation theory in the context of algebraic geometry. I should mention Grothendieck, Gabriel, Ekedal, Miyoka, Bogomolov, Brunella, McGill, Shepard-Brown, and many others. And a recent landmark achievement in this area was the classification of foliations on algebraic surfaces, algebraic foliations on algebraic surfaces. And one of our examples, the Hilbert-Moller surfaces, actually plays a special role in this classification. Okay, so let me now get to the other source of motivation, which was actually our entry point into the subject. And that has to do with inseparable morphisms in characteristic P. Okay, so let's suppose that we have an algebraic variety, two algebraic varieties, S and Y in characteristic P, and a morphism between them. Then we say that this morphism is of height 1 if it factors the Frobenius morphism from S to SP. Okay, so if I can complete this diagram by another morphism from Y to S, such that the composition is Frobenius from S to SP. And situations like that arise often for Shimura varieties in characteristic P. We'll see some examples today. Perhaps the simplest example is the modular curve X naught P. We all know the picture that in characteristic P, it factors or separates into two curves. On one of them, the natural map is an isomorphism, and on the other strand, the natural map is essentially the Frobenius map from that curve to itself. Okay, so that's one basic example where this arises in the context of Shimura varieties. Such situations also arise in the context of abelian varieties in characteristic B. I'll give you an example in a second. But before that, let me introduce a little bit more terminology. Okay, so the fundamental result in this story is the following correspondence due to Jacobson, who actually defined it in the context of fields and used it to create a sort of Galois theory for inseparable field extensions. But it can be easily promoted to the context of varieties, and it goes like that. Let S be a non-singular variety over a perfect field of characteristic P. Then on the one hand, we have foliations. Okay, so those are sub-Lie algebras of the tangent bundle that are also closed under P power operation. And on the other hand, we have finite morphisms from S to a target, which is a normal algebraic variety. And there's a bijection between the two. Okay. And furthermore, F is a smooth foliation, namely it's everywhere locally direct summand of the tangent bundle, if and only if Y is a non-singular variety. Okay, so this is a very powerful tool to study global geometry of varieties in characteristic P. In particular, we're interested in it because it complements other tools we have to study Shimura varieties in characteristic P, which are the local models, which, as the name suggests, provide very good local information, but are not that efficient in providing global information. So that tool of foliations, we are hopeful, would be kind of complementary to the use of local models. Okay, so we'll use the notation given a foliation, we'll denote this y by s modulo the foliation. And just a sketch of how do you get from foliations to y. Well, in some sense, OY is just the function on OX that are killed by all the derivations coming from F. Okay, this always contains the P power functions.
You have S and Y. What is X?
Oh, I'm sorry.
X is S, I guess.
X is S. Thank you very much.
Oh, okay. Okay.
Yes, notation changed as I was preparing the talk. Thanks, Joe. Right, so this always contains the P power function, so it's a rather big shift to begin with, so to say, and you add all the functions that are killed by derivations coming from F, and that allows you to go in this direction. Okay, so just to give a hint how this goes. And here's an example, in some sense, that's an example we all know, but it's reinterpreted in this language of foliations. So let A be an abelian variety in characteristic P, and let G be a group scheme, which is contained in the connected component of the P torsion of the abelian variety. Okay, so it's a local group scheme. And we let F to be the tangent bundle, the tangent space for this group scheme at the origin. Okay, that's contained in the tangent space of the abelian variety of the origin. But we sort of promote it to a foliation again by using translation by the group elements. Okay, so this tangent space as the origin now, by translating, gives us a tangent space at every point, and the whole thing fits into a subsheaf of T, which is closed under Lie brackets, etc. Then the quotient of the abelian variety by this group scheme is the same thing as taking A and dividing it by the foliation F. Okay, so just reinterpreting something that we use all the time in the context of abelian varieties and group schemes. Okay. All right, so as said, I want to present two types of foliations in the context of Shimura varieties. The first kind we call tautological foliations because they rest on the structure of the endomorphism ring. So we are in the context of PEL Shimura varieties. The second kind we call Vfoliations because they rest on the Verschiebung. They use the Verschiebung map very strongly. Okay, so let's start with the tautological foliations. Yes. Yeah, go ahead. Yes.
Can I ask something?
Yes, go ahead. Yeah.
In the context of the complex foliation, I can imagine that any foliation should have some kind of natural dimension, right? I mean, if you have the Frobenius theorem, you have the dimension.
Of course. Yes.
What kind of dimensions do you get in the setting in the characteristic P? Because once it contains the pth power of everything, it looks
as a subbundle of the tangent of the subbundle of the tangent bundle. It could be of any rank, of any dimension. It depends on the situation, but a priori it could be of any rank. And it's a locally free subsheaf. And for example, if you're dealing with an abelian surface, which is a product of elliptic curves, you can find here any things of any rank.
Okay, but if it contains OS to the P, then shouldn't it be of maximal rank anyway?
No.
Or it's unrelated?
No, it's not related.
Okay. Okay.
This has to do with the fact that Y, what you're saying, would have to do with the Y having the same dimension at S.
Yeah, something like that.
Yeah. Okay.
Okay.
All right. So as I said, the tautological foliations, my example would be Hilbert modular varieties, but I will begin with the example of a real quadratic field, so Hilbert modular surfaces. The general picture is generalization of what I'll explain for surfaces. It's just for surfaces, I can really kind of draw nice pictures and things like that. So I prefer to start with this particular example. Okay, so let L be a real quadratic field, and we're looking at the moduli space of principally polarized abelian surfaces with action of the ring of integers of L. The complex points of this variety is the upper half plane times itself, modded out by a certain discrete subgroup of SL2L that you can write this way. The precise definition is not so important. And we have two foliations. So at every point, the tangent space at every point is somehow in a natural way just C2. And we have two natural directions to go, if you will, which is this way or this way. This defines two foliations on the upper half plane. If you want to draw all the leaves, so to say, for the red foliations, this one, they're all sort of parallel to one of the axes. And because of the way this group acts, you could see that those foliations descend to the quotients and give you a foliation on the Hilbert modular surface. Those foliations extends actually to a toroidal compactification. So if you look at what happens at the boundary when you're doing a toroidal compactification, you have a chain of P1s appearing in the boundary, and near the boundary, those foliations, sorry, they kind of look something, I don't know, like that. In fact, what happens is that both components, so to say, or all components are integral subvarieties for those foliations, no matter which of the foliations you took. So it's an interesting phenomena that somehow the components of the boundary manage to be integral for both foliations. And those foliations actually are singular at that point, namely they are not anymore locally free of rank 1. Okay. So this is the type of picture that we get here for those foliations. Okay. Now, the only algebraic integral curves, that's something you can prove, are either the components, well, morally speaking, they're just the components that you add at the boundary in the smooth toroidal compactification. Any other integral curve that you had transcendentally actually remains transcendental when you go to the Hilbert modular surface. So it kind of keeps wrapping around forever. It's not algebraic. That's something you could prove. There are little caveats here having to do with elliptic points that I put in footnotes, but I really don't want to discuss them. It's just because I didn't want to use level subgroups here where there are no elliptic elements. So there's something going on with elliptic points, but it's really not essential to get into. Okay. So this is a transcendental description of foliations of Hilbert modular surfaces. It uses the universal covering space, which is H times H, the upper half space times itself. But in fact, you can define those foliations completely algebraically. Okay, so let's look at another way to define them. We let omega A be the relative cotangent space at the origin of the universal abelian surface A parameterized by M. OL acts on the universal abelian variety, so therefore at the cotangent space at the origin, and it actually factors it into a sum of two line bundles, which I'll call L1 and L2, depending on the two ways you can embed OL into complex numbers. And this is not such sort of esoteric construction. In fact, Hilbert modular forms of weight K1, K2 are just global sections of L1 to the K1 tensor L2 to the K2. Okay, so this is really something familiar that we are all working with. And the Kodara-Spencer isomorphism in this case gives you an isomorphism between the tangent bundle of the Hilbert modular surface, Hilbert Blumenthal surface, is L1 to the -2 direct sum L2 to the -2. And here, this actually works arithmetically. So I can really look at the moduli scheme of abelian surfaces with real multiplication and principal polarization. And we have this isomorphism. Okay. I'm using this isomorphism to define two foliations, F1 and F2. Okay, so F1 is just this, F2 is just this. Okay. Now, I'm saying foliations, but I'm actually slightly misspeaking because, well, one interesting feature is that they're defined integrally, but in fact, in characteristic P, they need not be P closed. Okay, so if I look at characteristic 0, those are just another incarnation of the foliations we defined using the picture of the universal covering space. In characteristic P, well, because the line bundle, the condition of being involutive, being closed under the Lie brackets or the Poisson brackets is automatic, but being P closed is not. And there's an interesting story happening, which I want to explain. Okay, so let us assume that P is split in the totally real field. And now let's consider those foliations in characteristic P. Then in fact, there are foliations, they are closed under this P power operation. And in some sense, they come from a Shimura variety with level P structure. Now, because P splits, P is a product of two primes in the totally real field, P1 times P2. Sorry, that should be POL. It's factors into a product of two primes. And there are two level sort of P Shimura varieties, as one associated to any of those primes. And the picture is like that. If you want to sort of visualize it, on the Hilbert modular surface, there's a stratification that I studied with Oort. There are two types of those two types of curves, tau1 and tau2. They are defined as the vanishing locus of two different Hasse invariants. They intersect transversely. So red components do not intersect with red components and blue ones don't intersect with blue ones. And the Shimura variety with level P structure looks roughly something like that. It has two horizontal components that intersect at the pre-image of this, this particular sort of part of the non-ordinary locus. The other part behaves differently for this particular choice of, so it looks like something like that when you go to the other part. Okay, so this one separates into two branches, one lying on each horizontal component. And the statement is that, okay, instead of telling you how those maps look like on the horizontal components, I'm telling you something which is equivalent to this, that you could think about this. So there are two horizontal components. One is so-called multiplicative, and it's just isomorphic to M, like in the modular curve X0P. And there's another component that they call the Eyal component. This component is related to M in the following way, that if I take M and divide it by the foliation F1, I will get the Frobenius transform of M0 P1 et al. Okay. Now it's interesting because this map is a map of the map from M to M modulo Fi is actually not the Frobenius map. It's dividing, it has rank P and not P square. So it's like half the Frobenius map. And this describes, if you wish, in a precise way, the tau component of this moduli space. Okay. Now, if P is inert, actually those FIs are not foliations. Okay, the picture is much more complicated in this case. Again, there are sort of the non-ordinary locus is divided into two components, but this M0P has actually two horizontal components that are related to M in a way which is either a either a Frobenius map or an isomorphism. They intersect along the whole supersingular locus, those two components. So it's a more complicated geometry, but it's much more complicated than that. Over each of those, there's also P1 bundle, vertical components that map completely, I mean, it's vertical over the corresponding curve inside M, okay? So this whole P1 bundle, that's a P1 bundle sitting over M, etc. And over those particular points that are the super special points, there are actually two different P1s, one coming from this P1 bundle, the other one coming from the other. Okay, so the geometry is kind of a very rich picture in this case. Okay. And the last case is what happens when P is ramified. In some sense, this is there's something subtle going on here. So in this case, the foliation is not defined everywhere, but so-called on the Rappaport locus of those Hilbert-Blumenthal surfaces. So the Hilbert-Blumenthal surfaces for P ramified are actually singular at finitely many points. Those are the non-Rappaport locus. There are certain, they correspond to certain super special abelian surfaces. And the foliation is not defined at those points. To define it at those points, we have to blow them up, and then we get those P1s. Those components that you see in this picture are meant to be components of the non-ordinary locus. There are P+1 of them coming into each such singular point. When we blow it up, those of course separate. And something that Andreata and me found a long time ago, that there's a certain interesting symmetry to those surfaces, namely that there is a map which is sort of a blow down map from this, once again to the Hilbert surface, that what it does, it actually takes those blue components now and shrinks them to points, okay, while this non-Rappaport locus that we had to blow up for the foliations actually now stays horizontal. So it becomes those components. Okay, so there's a beautiful symmetry to this whole picture. And in fact, once more, this is part of a gamma 0 P type of moduli problem. I think it's actually very much related to so-called those splitting problems studied by Papas and Rappaport. And the foliation is serving us also in this sense, that here I put this blowdown in quotes because it's not really a blowdown. To get a precise description of it, what happens is that you have something that looks very much like that, and you have a map from one going to the other, which is dividing by this foliation. Okay, this is an inseparable map of degree P. It's like a square root of a Frobenius morphism. And here, finally, there is a true blowdown. Okay, so those subtleties that you can't really see on geometric points are well explained by this kind of foliation structure. Okay, so this is the picture for Hilbert-Blumenthal surfaces, maybe even in too much detail. Let me tell you what happens more generally. Okay, so we just have to introduce a little bit more notation. So instead of dealing with a quadratic imaginary field, we deal with a totally real field of degree G. And to simplify the situation, I'm just going to assume that P is unramified in this totally real field. It factors into a product of prime ideals. Once more, we look at the moduli space of principally polarized abelian varieties with OL action. But I'm going to focus now on characteristic P. And as a notation, I'm going to look at all the embeddings of L into QP bar. This set decomposes into a disjoint union according to the primes P dividing P in OL. So every such subset I'm going to call B sub P, and Frobenius acts transitively on each such subset. Okay, the degree of BP, of course, is the number of elements here is the residue degree of the corresponding prime over P. Okay, and we have so-called the Hodge bundle. It's exactly what I denoted before by omega of the universal abelian variety. And as before, it decomposes into a dark sum of line bundles indexed by the embedding of L into QP bar. You can also do it arithmetically. You don't have to work locally. Okay, so analog of the Kodaira-Spencer isomorphism that we've seen before is that the relative tangent bundle of M over spec of OL decomposes into a direct sum of line bundles that are closely related to this. They are just those line bundles to the power -2. Okay, so the dual of LT raised to the second power. And that's sort of a handed, this decomposition is handed to us, and we're going to call F tau the corresponding component. It's a line bundle, so it's automatically involutive. Okay, and again, the main question would be whether it's closed under this P power operation when we think about F tau as derivations, as sections of this, as derivations of the sheaf of functions. We can raise derivations to a P power. The question is, if you take a derivation here, would it P power still lie there or not? Okay, so there's an interesting story that I want to present. Once more, it will involve a certain gamma 0 P moduli problems. And for every prime P dividing P, there is this moduli problem M0P. So before I didn't explain what it is, now I'm sort of coming clean and explaining what it is. It classifies, so to say, over M, the additional data of a group scheme contained in the Gothic P torsion of A. Okay, so I fix a prime P, then I define a moduli problem by parameterizing subgroups of this part of the P torsion of the abelian variety, the things that are killed by the prime ideal P. And I want them naturally to be OL invariant. That's the context we are working with, and also we'll take them to be maximal isotropic. So this is the definition of M0P, okay, of this level P. And as we've seen already for surfaces, it's a very complicated space. So one would want to find tools to understand its geometry. Okay, so here's the theorem. If you did this construction in characteristic 0, you will find that those are foliations, but the leaves are transcendental except at the boundary. Okay, so in some sense, this is of less interest to me right now. Now, generally speaking, such an F tau will not be a foliation. You have to sum all the taus corresponding to a Frobenius orbit of embeddings of the totally real field into QP bar. Okay, this is the case why for surfaces in the inert case, F tau was not a foliation. I would have to take, in that case, the two foliations F1 and F2, sum them together, but then I would just get the whole tangent bundle, which corresponds to the Frobenius map from the surface to its Frobenius transform. Okay, But those are foliations. In a sense, you cannot do better. Namely, if you take a subdirect sum of this, it will not be a foliation. And they're associated to this particular level P moduli problem in the sense that if I take it's a tau component, okay, that again, one can define, it means that this H here, the H that appeared here is a tau. So if I take the, where am I? If I take the tau component and take its Frobenius transform, this can be described as modding M by the foliation, which is the sum of those foliations from the prime ideals that are not P. Okay. So it gives us a way to access those level P Shimura varieties in terms of the original moduli problem that has no level P in itself plus data about its tangent bundle. And in fact, certain integral subvarieties of those are higher dimensional analogs of those blue and red curves that I drew before, are so-called, there are certain strata defined by Otto and myself, which can be described in terms of those partial Hasse invariants H tau. And in fact, those are the only ones that we know outside boundary components. Okay, so it's a very interesting problem, I think, to understand if there are any other integral subvarieties. Okay, so it's in some sense could be viewed as an Adre-Oort type of problem, but well, okay, I won't go more into that. Okay, so those are the only integral varieties we know that, and the obstruction for F tau to be foliation, namely, as I said again, this is a line bundle contained in the tangent bundle of M. The obstruction for it to be closed under the P power operation is this. Okay, so if you're dealing with tau that is equal to itself under composition with Frobenius, namely, if we are dealing with a prime of residue degree 1, there's no obstruction and we get a foliation. In this case, this BP is just the singleton sort of corresponding to tau, the singleton tau. And it's the same statement that if this holds, then this is a foliation. That's the same statement. But if tau is not of relative degree 1, residue degree 1, so if sigma tau is not equal to tau, there is a non-trivial obstruction, and we can show that's sort of a nice phenomena that this obstruction is exactly the square of a certain partial Hasse invariant, okay, which are those Hilbert modular forms in characteristic P that I defined years ago. They play an important role in the theory of Hilbert modular forms because they're responsible to all congruences between Q expansions of Hilbert modular forms. Okay, so maybe a very quick word about the proof or a particular aspect of the proof. So I was talking about the obstruction for something being a foliation. So by a lemma of Ekadal, actually, the obstruction can be viewed as a map between the pullback of this line bundle under the absolute Frobenius morphism of M and the tangent bundle modulo, this F tau. Now, if you remember, this decomposition had to do with Hilbert modular forms, and you can show, using results of Diamond and Casey, that in fact, this morphism, which is a priori something that lives here, must actually reduces to a morphism between L tau to the minus 2p to just one of the line bundles appearing here. Okay, and you take this to the other side. So you find that the obstruction is a certain Hilbert modular form, scalar valued Hilbert modular form of a very particular weight, this sort of 2p minus 2, if you will, which is the same weight as this partial Hasse invariant. Okay. So using they proved the result of certain non-existence of Hilbert modular forms of certain weights, result that was conjectured by Andreata and myself, and they actually proved a stronger statement. And using the result, we could actually determine that the obstruction lies exactly here, not just in here. And in fact, it has no choice but being a scalar multiple of this partial Hasse invariant. And then we're using some beautiful lemma of Katz about the Kodar-Spencer behavior in the formal neighborhood of the boundary to find that, in fact, this constant is just 1. Okay, so it's precisely the partial Hasse invariant, which is or the square of it, which is the obstruction for F tau to be a foliation. Okay, so all this fits very well with structures we already know. Okay, so those was tautological foliations. The strong tool was the action of the endomorphism algebra on the moduli problem of the universal abelian variety, therefore on the cotangent bundle, Kodar, Spencer, and all this stuff. There's another source of foliations which uses sort of a different, it comes from a different source, which is what we call Vfoliations, and that's what I want to discuss next. Okay. So this is, in a sense, a more subtle construction. It uses Verschiebung and very particular properties of the Gauss-Mannin connection. And while the tautological foliations were something we could discuss arithmetically, this is a purely characteristic P phenomena. Okay, so let me remind you that given an abelian variety of a characteristic P field, we have the relative Frobenius homomorphism from A to its Frobenius transform. And there's a morphism going in the other direction, which is the Verschiebung, such that the composition of those two is multiplication by P, either way you do them. In particular, I could use V to pull back differential forms from A to AP. Okay, and that's something I'm going to use in a second. Okay, so once more, I begin with the example of surfaces where it's a little bit less technical. We have a quadratic imaginary field E that appeared a lot actually in this conference. M is the moduli space associated to GU21, if you will. It parameterizes abelian threefolds with OE action. And I'll take principal polarization, although that's not important as long as P is prime, relatively prime to the degree of the polarization. MC is the Picard modular surface. And I think actually that nicely connects to this conference because of Steve Kudla's and Jim Cogdell's very first papers that had to do with the Picard modular surfaces and the compact analog and analog of the Hirzebruch-Sagier theorems in that context. Okay, at any rate, we choose a prime which is inert in this field, and we consider M, I'm changing notation and simply consider M over the residue field of OE, which is a field with p-square elements. In this case, there's no obvious construction of foliations coming from characteristic 0, in fact, and that's why we sort of need to introduce a new tool to define foliations. Okay. Now, we have the universal abelian threefold A, and it has its sheaf of relative, or its relative cotangent bundle, omega A. It's a rank 3 vector bundle over the moduli space, and the action of OE on it decomposes it into a sum of 2 vector bundles. P, because it has rank 2, the 2 has to do with 2 appearing in the signature, and L, suggesting it's a line bundle that has to do with 1 appearing in the signature. Okay, so there's the decomposition of omega A this way. And this is the Kodar-Spencer isomorphism in this case. P tensor L is isomorphic to the relative to omega 1 of the differential of M. Now, the pullback map that I mentioned before on differentials, okay, so this P lives inside omega A, And the pullback map on differentials from omega A to omega AP, I can restrict it to P, and it has a kernel, which I will denote PV. Okay, so those are those differentials that we kill by V. And I could take this PV, which would be a line bundle in this case, okay, tensor it with L. Okay, so this now lives somewhere inside this. So this whole tensor product lives inside omega 1, and I'm going to take its perp under the natural pairing between the tangent bundle and differentials. Okay, so I'm going to get a line bundle sitting inside the relative tangent space of M. And this is the foliation in this case. Okay, that's its construction. Okay, so a theorem, which is funnily enough, we started, our interest in this subject started several years ago and started with a more complicated construction, and more recently we arrived at those tautological constructions. Okay, so the story is kind of a little bit reminiscent of what we've seen for Hilbert-Blumenthal surfaces at bet primes. This foliation is defined on M everywhere except at the superspecial points. Okay, so on the surface, there are those finitely many superspecial points, and there's the complement of the non-ordinary locus. Actually, there are many components coming in here. Okay, so draw it maybe like that. It's defined everywhere except those green points, the superspecial points, in particular on every supersingular, this supersingular curve that comes. By the way, this was studied by Ink and Follard in her thesis. She determined that each component of the non-supersingular, of the non-ordinary locus is actually a Fermat curve. There's a very nice global description of what's going on here. But this foliation is not defined at this point, and to make it well defined, you have to blow them up. Okay, and then those curves will kind of separate this way. Okay, this blow up, the foliation is defined. You could ask, what are the integral curves for those foliations? What are the curves whose tangent bundle is exactly described by the foliation? And we could show that the natural Shimura curves living on this Picard surface in characteristic P, those coming from U11 actually are integral curves, except as well as those components of the non-ordinary locus. And we conjecture that there are no other integral curves on this surface, no other algebraic curves that are integral for this foliation. Okay. There is an M0P moduli problem associated to this that has sort of an étale horizontal component and a multiplicative horizontal component. And it's rather hard to draw. Okay, so if I wanted to draw this moduli problem, this M0P, the best I can do in real time is basically give you the things you need to glue together to get this M0P. So there's one copy of M0P, which is the multiplicative component, which is just this blow up of the base moduli problem at the superspecial points. There's another component which is rather similar to it in the sense that this étale component of M0P is this M sharp divided by the foliation. Okay, now this is interesting because this étale component is actually is not sitting finite flat. Those points were blown up to get M sharp. Okay, so this is something nice that we can do with the foliations. M0P étale generically is easy to understand over the sort of the mu ordinary locus. But if you want to understand it globally, namely if you take the Zariski closure to get a component, it actually doesn't map finite flat anymore. It's essentially the blow up of of M. It's essentially M sharp, but to be more precise, it's M sharp divided by F sharp. Okay, so you have those horizontal components, but besides that, there's a lot of other stuff that goes on. There are sort of P1 bundles, many P1 bundles that are sitting horizontally over the base moduli problem with no levels P structure. And in fact, over super special points, you have sort of like comps of P1. Okay, so this is certain comps of P1. So if you have to take all this stuff and glue it somehow together to understand how the base moduli problem looks like. So those comps of P1 map into to those points. Over those curves, you have those P1 bundles that you have to take into account. And then there are also two more horizontal components. Okay. So over the general point, over the mu ordinary locus, those are not really ordinary abelian varieties. That's why the mu appears here. But nevertheless, over the mu ordinary locus, there's another way you could construct foliations a priori, which is using Ben Monen's generalized third-Tate theory. Okay, so this comes from understanding the deformation theory of those abelian varieties with OE multiplication. And this deformation theory suggests another construction of foliation, and we show that it agrees with our construction. And another fact to mention is that in another work, we define a theta operator on Picard modular forms. And we can show that this theta operator, in a certain sense, is taking derivative of Picard modular form, but only in a particular direction, okay, which is the direction of the foliation that we defined. So I really don't have the time to explain what I mean here. It's just a hint that this connects to Picard modular forms and this theta operator, which is important for understanding filtrations of Galois representations. Okay. Okay, so let me see what I can reasonably say in the remaining 3 minutes about the general case. So there is a theory for the general case for the unitary Shimura varieties of signature MN that appeared in this conference already several times. So we take signature where M is less than N, because if they're equal, we don't get a foliation. Okay, so the M is less than N, they're associated to quadratic imaginary field. There's a universal abelian variety living over this moduli problem that lives over OE. And once more, the relative cotangent bundle of the origin of this universal abelian variety decomposes because of the action of E. Now into two pieces that are vector bundles of rank N and M respectively. Okay, so P and Q, and once more we have Kodaira-Spencer. We have again the Verschiebung morphism that allows us to look at the map of differentials of A to its to AP, and we take PV, the kernel of that, and once more by exactly the same machinery, this PV tensor Q lives inside omega 1, and we could take its perp in the relative tangent bundle of M over K, and that's F. Okay, that's what we call F. By construction, it's a sub vector bundle of the tangent bundle of M. And likewise, there's a level P moduli problem associated to it. So I was trying to be more precise about what it is, but in the interest of time, I'll skip this precise description and just say what the theorem is. So what we constructed the theorem is that it's a foliation. And it agrees with the deformation theory of ordinary object, which is coming from Monen's theory of generalized third-Tate parameters. It also agrees with a theta operator on Picard modular forms. We have some information about integral subvarieties. There are a particular Ekadal-Oort stratum that we can describe very precisely. And once more, this foliation does not exist everywhere. It actually exists on a certain part of the moduli problem. Like for surfaces that we had to blow up to super special points, here there's really a subvariety that you have to blow up and to define the foliation, and that's what we call M sharp. Only there the foliation exists. And it's interesting because you really need to do this modification of M, this blow up, to understand this Shimura variety with level P structure. Okay, so the theorem is that once you blew up M to extend the foliation, you can now divide by it, and that defines the tau component for this gamma 0p level structure. Okay, so perhaps I'll just mention a theorem proven by my PhD student, Reginald Libert, that actually shows that any Ekadal-Oort strata, that this foliation actually induces a foliation on any Ekadal-Oort strata on which it's defined. So that means that we can understand how Ekadal-Oort strata are behaving under this map from M0p, the gamma 0p moduli problem for unitary Shimura varieties to the base unitary Shimura varieties. Okay, I wanted originally to draw another picture, but I'm out of time, so I'll finish here, and thank you for listening.
All right, does anyone have any, well, we're still clapping. Okay, does anyone have any questions or comments for Eyal?
I'm wondering, when can Shimura subvarieties in characteristic zero be integral subvarieties or leaves of a foliation?
No, there aren't. So, for example, well, for the Picard example, we don't really have foliations in characteristic zero. It's purely a characteristic P construction. I mean, you could think about other things, of course, like totally geodesic submanifolds in the sense of Kudla-Milson and things like that. I'm not talking about that. But if you look at the Hilbert modular case, you had the upper half plane times itself, and the foliations were really kind of those kind of either this way or this way, the horizontal leaves. But if you look at the, for example, the twisted modular curves that map in the Hilbert modular surface, they really go, they're like going like that. Okay, so there aren't.
So there's no foliation that has that as a leaf, even if it's the only one.
Well, that I don't know. The thing is that foliations exist in abundance, okay, especially in characteristic zero. So for example, if you take a surface in characteristic zero, well, what are you asking? You're asking for a subbundle of rank 1 of the tangent bundle. Mm-hmm. And you just restrict to some Zariski open neighborhood where the tangent bundle is trivial, and you take any line bundle sitting inside it. Because it's a line bundle, it's automatically involutive. So you're done on this open Zariski open neighborhood. And there's no other requirement of being P closed in characteristic zero. And then there's a general principle that you can always extend foliations if you allow singularities. Mm-hmm. Right? So in some sense, you can, there's so much, so to say, too much freedom in this construction. So the interesting thing, of course, in this business is to try sort of find foliations that would teach you new things about the geometry of the Shimura varieties.
I mean, if the signature is not n minus 1, 1. What was this exceptional locus?
Yes, so this is so-called, we call it M4. Okay, it's a name we invented, so I don't expect anyone to know what it means. The thing is that the Ekadal-Oort strata in this case are sort of parameterized by NM shuffles. Okay, so it has to do with the structure of the Weyl group in this case. So those are permutations sigma in the symmetric group with m plus n letters. And so a shuffle means that if you write your permutation as say 1, 2, up to n plus m, then the numbers, when you start writing the image under the permutation of 1, 2, up to n plus n, the numbers between 1 and n will appear in order on the bottom row, not necessarily consecutively. So it could be something like, 1, 2, 3, etc. up to n. And also the numbers from n plus 1 to n plus 2, they will interleave with, up to n plus m, they will interleave with those, but will appear also in order. Okay, so that's a shuffle. And in this language, this M4 is associated to a very particular shuffle where it's the shuffle where you have 1, 2 up to n minus m. Then it changes to, let me choose a different color. Then you have n plus 1 up to n plus m. And then it continues with n minus m plus 1 up to n. Okay, so it's a very particular, permutation, very particular shuffle corresponding to a very specific Ekadal-Oort strata. Okay. So every Ekadal-Oort strata that contains this in the boundary, the foliation is defined on it. And maybe I should mention that it's a very, if you draw the picture of Ekadal-Oort strata, it's a very complicated diagram, even for those simple Shimura varieties. Okay, so if this means going to smaller strata, okay, so it could be very non-symmetric diagram, and so on. So somewhere here, there's this S4, M4, a particular Ekadal-Oort strata, and everything containing it in its boundary has the foliation is defined on it. But there could be strata of rather high dimension. In fact, there will be at least of codimension 2, but they could be of codimension 2 on which this is not defined. The foliation is not defined. So yeah, that's the picture. The UN1 case. So if you just allow me to expand on that, it's a very interesting example. It's a very pleasant example where the Ekadal-Oort strata are sort of linearly ordered in the UN1 case. And the foliation is defined everywhere except at the lowest strata, which are finitely many super special abelian varieties. And if you need to blow only those up, so you'll get a projective spaces as the exceptional divisor, and then the foliation will be defined everywhere. And if you divide this blow up by the foliation, you'll get the tau component of this gamma 0p level structure.
Okay, thanks.
All right, do we have any more questions or comments for Eyal?
So
Yes.
which level structure are you? So you mentioned maybe you skipped that page. So which level structure for the
Yeah, that
modular problem?
it's the tiny bit. Sorry, where was it? It's a tiny bit technical. So so the sort of part of the data is rather obvious. So you're taking H containing the P torsion that are always stable, isotropic. Okay, that's expected. But the rank here would be P to the 2m, where m is the smallest, smaller signature. Okay, so we're not attempting to get to the maximal possible. It's P to the 2m. And you require it to be Renault. So this is a condition that we actually learned from Belaish's thesis. This condition to be Renault can be phrased a la Renault in terms of how the augmentation ideal for this group scheme look like, but you can also phrase it in terms of the Dieudonné module. So if you take the Dieudonné module of such a group scheme over any geometric point, this Dieudonné module has an action of OE because it's an OE stable group scheme, and it decomposes into a direct sum of two modules according to the OE action. One we call this one the sigma part, and the other one is the sigma bar part. And you want them to have the same dimension. That's equivalent to Renault. And the reason is the same reason that Michael Rappaport mentioned this morning. You have to put such conditions to avoid, to get a flat moduli problem. Otherwise, you'd get some extraneous components in characteristic P, some abelian varieties that actually cannot be lifted to characteristic zero. So you kind of, you throw them away by introducing this Renault condition in this case. So this is necessary for the unitary, in the unitary case, but in the Hilbert modular case, for example, there's no need to do that.
Eyal, may I just add that this can be checked to be the same as the Ivahori integral structures that are defined, I think, in chapter 6 of the Rappaport Sync book.
Mm-hmm.
Yeah, so I mean, that's in terms of the modeling problem. We like it this way, but it can, yeah.
Yeah, it's, yeah, good point. Thank you.
I have a question. When you have this decomposition, when you have in general case of U and M, you have this decomposition into P and Q, and you take the restriction for the Verschiebung foliation, you take the restriction to one of them. Is it a given one, say one of the smaller dimension or one of the larger dimension? And if you can take for both, what kind of symmetry you have there? By the kernel of Verschiebung one, kernel of Verschiebung of the other one.
You take it for the larger dimension.
So if you take on for only one, then you can't discuss any symmetry because you don't, because the other is irrelevant. Or you can say something about the one with the low dimension as well.
With the low dimension, okay, so now you got me. At least for the Picard modular surfaces, when you take the low dimension, you'll get everything, so to say. So you'll get, where am I? Yeah, so when you define the foliation, you at least for, sorry. Just looking for the definition, yeah. At least in the case of surfaces, so if you try to use this Q instead, you take the kernel of Verschiebung on Q, you'll get Q itself. Okay, so here you'll get the whole omega 1, and here you'll get 0, which is not necessarily uninteresting. I mean, but yeah, I mean it's rather a trivial construction. In the higher dimension case, yeah, I don't remember offhand. Maybe Udi remembers if it kills Q also in the higher dimensional case.
Yeah, no, I think we checked it.
We checked it, yes.
The only construction is going from.
Yeah.
By higher dimension, you mean UN1 for any n, or for UNM for every n and m?
For every n and m.
For every n and m, yeah. Yeah.
Okay. Well, just
Yeah.
one.
Yeah, no, it's a good question. It's a good question. I just didn't
But it has a simple answer.
remember. Yeah. No, as Udi said, if you took the kernel of V from Q on Q, it will be the whole of Q. So if you're trying to do this, you'll have P tensor Q, which is the whole of omega 1. So you get something trivial. Yeah.
Thanks.
It's nicer to have an older co-author who can remind you.
Great, thanks.
Yeah.
All right, are there any more
Yes.
questions or comments?
Can you say why m equals n does not have foliation?
Yes. When m is equal to n, actually the general abelian variety is ordinary. So you're not going to get the only thing you'd get by that is something trivial. Right? So I guess in this case this PV would probably be 0. And here you'll have the 0 thing, and its perp will be the whole TM, which in sense might be not uninteresting. I mean, it could be, we need to check that, but it sounds reasonable that in that case, you'll get that this M0P it's a tau component is like the Frobenius transform of your base Shimura variety, okay? But from the point of view of getting non-trivial foliations, you're not going to get something in that case. Okay. Also, the thing you.
Oh, sorry.
Yeah.
Go ahead. I didn't mean to.
No. You go ahead.
Maybe I should let you finish what you were gonna say. I was gonna ask more about this M0P tau component.
No, I was just meant to say that when m is equal to n, or if p is split, actually the general point is an ordinary abelian variety and not mu ordinary. And in this case, if you're trying to do something just on the ordinary locus, you could ask yourself, well, what happens for those general abelian varieties? So when p is inert and m is less than n, there's this deformation theory of Monen of cascades that suggests that when you're looking at the deformation of those mu-ordinary abelian varieties, there are preferred directions. It's the deformation space just has this particular structure that picks up preferred directions. But when m is equal to n, or p is split, the general abelian variety is actually ordinary, and this theory just amounts to the usual third-Tate theory, where the formal deformation space is a formal torus in which there's no preferred direction. Okay, so that's another reason why you won't get anything sort of interesting out of it when m is equal to n or p is split.
So is this where you mentioned something about Monen's or maybe someone else's geodesic, like total or geodesic subvariety or something like that?
Yeah, Monen has this theory of cascades or generalized third-Tate parameters that is used to study the deformation theory of general points of Shimura varieties when they are not ordinary. Okay, so it's a much more complicated structure. It's not a formal torus anymore, like in the case of the Ziegel modular varieties. It's a sort of, in the simplest case, it's kind of a bi-extension of two p-divisible groups by a torus. That what happens in the case of U2-1. In general, it's a whole cascade of p-divisible groups that are composed together to describe the deformation theory. But in case of U2-1, there's a certain structure of bi-extension of 2p divisible groups by a torus, and that torus that sits there gives you certain preferred directions in the unitary Shimura varieties, and we show that it agrees with the foliations we defined. But one advantage is that our definition already gives an extension of the foliation deep inside the Shimura variety, which is not something you can get from Monen's work.
Oh.
Yeah.
Okay, let me stop here because and let people go if they need to. I'll let Siddharth put the